So hello and welcome to our panel this morning on cleanliness testing. Increased miniaturization, 5G, forthcoming 6G, and EV reliability are all driving demand for more accurate, reliable, and data-driven cleanliness testing systems. This panel will discuss the alternatives and best practice. I'm delighted to be joined by Mark McMean from STI Electronics on the end there, Jason Keeping from Celestica, and of course Mike from Bixen from Magnalytics, actually. I was going to say Kaizen, but Magnalytics. So thank you for joining me this morning, gentlemen. Let's get straight in with the first question. And I'll give it to you, Mark, on the end, which is, has the requirement for cleaning before coating increased with the rise in electromigration in miniaturized devices?
Yes, Trevor. What we're seeing is a need to make sure that we understand the cleanliness level before we do conformal coatings and pottings. We're actually starting to see more and more units needing to be protected in their environment, especially as we go to 5G on the telecommunication side, but equally so in the industrial markets. As the miniaturization gets tighter and the densities get smaller and we get really, really tight, now becomes the need to make sure that we get really good cleaning and that before we put in any of our conformal coatings and pottings so that we can get the reliability. We have been noticing this trend over the years continuing to increase, but it's really starting to take a major move and acceleration as well as with just traditional conformal coatings, but also with the new addition of the nano coatings. Right. The nano coatings are also needing to make sure that they're ultra clean before they're put on, because nano coatings by their very nature are thinner. And you need to be there. So IPCs identified that by putting in their J standard, the Section 8 cleanliness requirement, and the ability to get objective evidence. So we're seeing this whole trend start to take fold and take acceleration, and you'll see in the coming 3 to 5 years that this will become even more of a need in the industry.
Right. And is this happening across specific applications like 5G communication boards, or anywhere there's just a lot of miniaturization into the assembly?
That is correct. So on the 5G side, you've got to make sure that at these higher frequencies that you don't have any interference in the RF signal itself. And it doesn't take very much to influence it. Yeah. We have worked with 2 of the 5G transmitter guys, and what they found is that cleanliness does impact their overall ability to transmit and receive, and thus that has grown into it. And remember, everything is getting smaller, lighter, faster, and the density is greatly shrinking, so that it becomes easier for us to have a little bit of contamination influencing the performance of these modules. And they're really a module is what it is.
Right, right. Now, Jason, you're manufacturing every day, making these things. Are you finding the same challenges? Are you finding the same results?
Yes.
You're having to clean more?
Yes, exactly what Mark was just saying. And it's really the design tolerance. So as things are getting tighter and tighter, the overall equation of causing corrosion, the electrical currents and all spacing, so now everything's closer together, so any contaminant, anything that is now there will actually cause failures a lot faster. So now that cleaning is not because of higher power or worse environments, it's just because everything is now compact, you get a lower space to travel to cause for failures. Right. So we're seeing it across all markets.
Yeah, that's an interesting point. I mean, we've talked many times, Mike, about design for cleaning, and you think that's becoming more and more important as we get smaller. That designers have to be kept in the loop and need to be informed so that they can make the right design decisions.
Yes, absolutely. One of the areas that we see with the miniaturized components is they're leadless, so they're bottom terminated. The problem with bottom terminated components is that they sit directly onto the board, so you have a really small gap from the board surface to the bottom of the component.
Right.
What we found is that as that component sits on the board, the dynamics of the flux package and the solder paste changes. And as it changes, it changes because in many respects, you can block outgassing, and in certain pockets, you can actually create conditions where you may leave excess solvent, you may leave excess activator. So, as things get smaller and we start to see, these designs that are cheaper, one of the areas that has been a great challenge to reliability has been the gap off the board.
Right.
And, as designers, if they looked at different components to where they built them to where they stood up, it only takes maybe 50 microns addition of a gap. It would make a huge difference. You'd have less residue. If you do clean it, it would be easier to clean, and you would have higher assurance that you would properly outgas that material.
So what would you say would be the optimum height? It should be at least 1 mil.
It really needs
allow
to
you
be
to clean
50
under?
to 75 microns is where you're starting to get acceptability. When you start to get down to 1 mil, which is 25 microns, it's you're really starting to create a condition where it's almost like the flux builds up on itself. And when you look at like an open comb test board, I'll show you an example, one right here, where you have uniform sheet resistance and you get proper outgassing. The residue stays very compact next to the circuit trace.
Right.
But when you lower that gap, and you start to almost underfill these components to where now back to what Jason was saying, you start to bridge the conductive paths with flux residue, which creates a greater chance of electrochemical reliability.
Okay, right. Okay, I'll move on to my next question. I'll go back to you, Mark, and that is, are certain substrates and board finishes susceptible to electromigration issues?
Yes, Trevor, what we're seeing is things like immersion silver and immersion tin in certain environments, especially sulfur dioxide environments, chlorinated gases. They're very susceptible, to creep corrosion, which starts the corrosion reaction, and then ultimately, with enough humidity and moisture, actually start to grow dendritic.
Right.
Or electrochemical migration events. So in some instances, it's a lower cost that's driving it, but you got to really choose that finish based on the environment that it's really going to be working in, right?
Yeah.
So industrial clients, military clients, aerospace, those guys are always looking at what their end environment is. But yes, the answer to your question is that you need to choose your finish for the environment that you're expecting. And the two that I mentioned, immersion silver and immersion tin, are vulnerable to both chlorinated and sulfur-based gases, which promotes creep corrosion and then the actual ECM event.
Yeah, okay. Jason, have you anything to add to that?
So I think complementing what Mark was just saying is, one thing is the workmanship of the solder mask. So a lot of big things are looking at surface energy.
Right.
So if the solder mask is still too low after being processed, what happens is after it gets conformal coated, it actually will delaminate. Then now there's an air pocket where now it almost creates a little environment to cause corrosion to go faster.
Yeah.
So if the conformal coat is applied correctly after cleaning, but if you've got this pocket now, it's basically an area which will entrap any contaminant, and then any moisture that comes in, it's almost like an incubator to cause this corrosion even faster.
Yeah, absolutely. Yeah. Good. Well, I think they both answered that, unless you've got something to add.
No, I think we're good.
Yeah. So my next question I'll give to you, Mike, and that is, has automatic bath monitoring systems improved reliability in board assemblies?
They have. The purpose of, especially when you're cleaning, is that what you're looking for is consistency over the life of the wash bath. These chemistries today are designed to work, and they're designed to hold soils, and they can stay in a cleaning machine anywhere from 30 days to 6 months to a year.
Right.
And so when you start to think of controlling that wash bath, what you're really looking for is consistency in the process. If you get a drop in, if you bring a lot of water, you lower the concentration, you can change the cleaning effect. Conversely, if you lower the concentration and it's not controlled properly, you can start to see some of the non-volatile residues kind of fade out of those cleaning materials, which could become a reliability issue. So controlling that bath to a point where you can keep it tight over the life of the process, you get better repeatability into the process. So as we start to see, you know, the cleaning tools that are out there today, there's been continuous technology on both controlling, but also yesterday there was a presentation on better monitoring the carbon ion exchange on the rinse side.
Okay.
So I often think about it, it's really a process. And if you think of it as a process, and if you think of all the inputs and the outputs and how to control those, you're always going to be better off.
Right. And do you monitor the baths?
Yeah, and I think the only thing to complement what Mike was just saying is, as you're saying about bath analyzers, they're process controls.
Yes.
So anything you can do to inhabit and make it more robust, you're making the process more stable, then any fluctuation between the process, the waters, the variables, they all get controlled and the outputs become much better.
Yeah, absolutely. Okay. Okay, Mark, put you on to my next question, which is rose testing useful as an early warning indicator of a drift in the cleaning process?
Yeah, Trevor. So rose has its place on being able to tell gross contamination. It's not going to do a good job at being able to measure things up under bottom terminated components, because rose is all about the dissolution of those cations and weak organic acids and anions into solution so that you can run them across a conductive sensor. Then that's the problem with rose is that it's good in only certain types of chemicals and ions and weak organic acids. So rose has its place as a gross contamination tester. A better means is ion chromatography, SIR testing, where you get an electrochemical signature, and it's measured up underneath the parts.
Right.
So the industry is moving to these different tool sets, but to address it, rose is not the only tool that allows you to pass or fail anymore. You've got to have objective evidence on a different set of tool sets, such as what I mentioned on IC and SIR. But you're seeing an awareness of using more tools and getting at the source. And the source is, am I clean underneath my components that are challenged, my bottom terminated, my LGAs, my micro BGAs, my chip scale packaging? Those are the things that are driving the industry now. And the rose is blind to those types of site-specific contaminations, where the other tools are starting to delve into that specific region.
Right. And I think obviously SIR testing is it brings off a lot more data and things like that.
Right, and that's a really good point, Trevor, and I'll let our other colleagues speak to it. SIR allows us to get an electrochemical signature that now gives us a data point that we can measure and we can reference, and we can then judge it as a baseline against future runs and things of that nature. So not only is it good for developing a qualified manufacturing process, but that data is also good for being able to set up a process control.
Right, yeah. So, I mean, you do a lot of work with SIR. Would you agree with that?
Yeah, I think Mark said it very well. I mean, even we've created IPC white papers talking about the integration of the subjective evidence.
Yes.
So all these process controls have been in place for a while, and they will show you a drift, but then what does that drift mean? Where the SIR is a much more critical data point, IC gives you more ionics, so you can figure out what is the source of these failures. What is it changing? But now with the objective evidence, now at least you've got two data points, it's not only one, to say that a process is in control.
Right. Okay. Now, Mike, with the systems you have at Magnalytics, you've made SIR testing a lot more easier and easier to understand and implement. How important is custom coupon design in SIR testing?
Well, one of the areas that we've tried to make a lot of advances in is to try to build test coupons that are really truly representative of the hardware that's being built. And in looking at that, there has been commonly in SIR testing, for example, when you characterize a material, the B24 test board has been commonly used, and they use an open comb test pattern.
Okay.
And in an open comb test pattern, you get uniform outgassing. You get uniform during the reflow, and so your material, if you're running a no-clean material, it's very benign.
Right.
It'll get very good SIR results. One of the areas that we've tried to look more attentive toward is to make dummy components and test boards that are more component specific with the type of components that you have today. And this particular test board has a couple innovations. One, we build them in 4 quadrants.
Right.
That way, when we test them, we can compare them. Some of the test boards that, like the B52, you can have 16 different channels. When you look at a graph on 16 different channels, you got a lot of different data. So we've tended to go toward smaller number of channels. But one of the areas that we've also done is, you can see on this test board, is an innovation and a patented technology by Honeywell, where they basically built glass dummies, and they use a thin film process to metallize the dummies. And what's kind of nice about these is that as you put them onto the test boards, you get a visual aspect of the residue set. So if you're going to clean it, you can see it visually. If you test it, you can see where the leakage currents actually take place with it, through the components. So there's different areas that we have always tried to continue to innovate. And then one of the areas that we've also tried to look at is that is the idea of the electrical twin.
Yep.
And what we're thinking about in electrical twin is a test board that can be patterned into the waste area of a panel of circuit cards.
Okay.
And the idea there is that if you have a test coupon that's in that panel, it's actually seeing the actual process conditions.
It's going through the same conditions. Yeah.
That's exactly correct. Yeah. And you could utilize this electrical twin with any of the different test methodologies that you wanted to use.
Right.
We build them to where we route them to where they can be SIR tested. But the nice thing about doing that is that they can be barcoded for traceability. You're not using production hardware. And just like what Jason was saying, you get to measure drift into your process over the course of time. Did something change in your process? If it did, you can address it. So part of the area of the test boards is trying to continue to address this area of objective evidence and ionic process control, and how can we do it better?
So how does this work then? I mean, the designer completes the design for the board, sends it to you, and you then look at where the challenging areas might be and design a test coupon that might go on the side of that board. Is that essentially what you do?
Yes, at Magnalytics, one of the things that we've done there is we provide the whole product. And what's interesting about the company is that it's a company that's owned by STI and Kaizen Corporation. Well, STI has all types of capabilities. So they have designers on staff. And so they understand, the electronics piece. And so one of the things that we do is we work with customers and we do the designs. We'll build the design that they can place into their panel to actually utilize that. And then on the other side, once we have those test coupons, we basically, it's kind of a free rider on their panel. But if they need dummy components, we can supply those. Or in some cases, if they have their own dummy components, they can utilize them. The real key to what we're trying to do is we're trying to help better address the problem in a way that allows them to have the best overall data within their process, to be able to monitor their process.
Right. Yeah. Well, that's quite a significant improvement, and I think, as you said earlier, it behaves differently when you apply the process to the open comb systems versus when it's got essentially an encapsulant on it or it's an overmolding. So it's good to be able to see how it performs using this glass system. I mean, it's pretty good. Mark, going back to you, what improvements do you think are needed to improve the cleanliness testing in 5G boards?
Yeah, we're seeing it. As they go from 5G to 6G and everything is getting tighter, and as Jason mentioned earlier, this spacing is so tight, it doesn't take very much to influence the performance of either the receiving or the transmitting of these 5G signals or 6G signals. So what we're seeing is the companies that are building it are testing and seeing how they're performing in real world, and they are coming to the realization that they've got to get things cleaner. And thus, there's a whole emphasis on making sure that there's very low ionics on the board that could influence it. So they're looking at all types of chemistries on the cleaning side, as well as on the flux side to make it easier. So we're seeing this convergence of making sure that we have engineered chemistries that are specifically addressing the residue pool for getting it out from under these parts, and aiding in that ability to get it ultra clean.
Right.
And then what they now are doing is working on 5G and 6G testers, so that now that when they test their performance, they can see how well their module is performing, and thus they can make an adjustment to their processes. So instead of just throwing it over the fence, we're seeing a lot larger convergence where the System Design Authority is wanting to address cleanliness on the front end, so it addresses the performance.
Excellent.
And that's being driven by some of these, not just in the 5G world, but also in the military and aerospace world.
Yeah.
We're seeing that. And Jason's another,
Advocate.
good voice on understanding what it takes to get something that clean.
Okay. Anything you want to add to that, Jason?
Yeah, so I mean, right now, when you look at it, a lot of the current users really in cleaning have been the aerospace, defense, military, high reliability. But now as we're going to other markets in telecom enterprise, 5G technologies, they don't have that same historical background for it. So now there's a lot of lessons learned, a lot of information that needs to come up, because maybe the component sets have not all been designed for cleaning. So now there's a lot of lessons learned that need to now accomplish to make sure when they go to clean, there's not some negative reactions that are going to happen.
Right. Final word to you, Mike.
Well, I think, as we look at this whole industry and where it's transitioned, within the electronic space, it's always innovating. Things are getting, we think about the electronics, and it's the largest industry in the world, and it just continues to make amazing products.
Yeah.
Our challenge on the manufacturing floor is to try to follow the innovation. What can we do? And the innovation brings opportunity. So what can we do within that space to help solve the problems? And just like what your interview today of us is that we're looking to say, okay, we see these challenges. Now, how do we address them? How can we address them in a better way and improve the process? And not only improve process, but if you improve knowledge within the process, you actually make the processes more cost efficient over the course of time.
Yeah, absolutely true. Well, we've had a great debate today, guys, and a lot of very useful input there. So I want to thank you all for your contributions. Mark McMean from STI Electronics, Jason Keeping from Celestica, and of course Mike Bixenman from Magnalytics. So, and I want to thank our audience for watching and joining us today.
Global SMT and Packaging opens the windows of the world to bring you the latest news and technologies from Munich, from Bangalore, from Shanghai, from San Diego.